This is this is homework 11, review problems for the final exam, and I will go over the review problems. So problem 1, compute some numbers as a decimal. The fifth root of e to the fifth, so exp of 5, is e to the fifth plus pi, you have to use a capital P, p to the fifth, and we want to take this number and raise it to the fifth power. Oops, sorry. We want to take the fifth root. So we want to raise it to the 1/5 power. And see what it looks like as a decimal. 3.4. And we have an iterated set of powers of 3. 3 to the 3 to the 3 to the 3 to the 3. Ooh. It's too big. Overflow means it's too big. Let's see if we can write this as a decimal. Huh. Interesting. So suppose I take away one of these powers of 3s. Still too big. Interesting. 3 to the 3, of course, is 27. 3 to the 3 to the 3, that's 3 to the 27th. But 3 to that power, that's too big. Interesting. So we see a limitation on how large the numbers are that you can put into Maple. Okay. Problem 2. Find all solutions of the following equations or systems of equations. So the first is simply solving a linear equation. Solve 5 times x plus 12 equals 11 times x minus 6, comma, solve for x. And the answer is 3. When we have the quadratic equation, solve x squared minus 11 times x plus 5 equals 0 for x. We get these two solutions. And if we wanted the solutions to be given to us as a decimal, we would use fsolve instead of solve. And these are the numbers. The third part of this problem is to solve a system of 2 linear equations and 2 unknowns. 6 times x plus 13 times y equals 100. And 9 times x minus 2 times y also equals 100. So those are the answers. And again, if we had wanted the answers as a decimal, I could have used the fsolve command. And those are the solutions as decimals. And the last is to solve a trigonometric equation. Now, I suspect we won't be able to get a solution using solve, but let me just try and see what happens. So we want to solve the equation cosine of 2 times x plus the sine of 3 times x equals a half. And x between 0 and pi. X equals 0 dot dot pi. Let's try fsolve. We get an answer. At least we get one answer. If we were curious how many answers there are, just to make sure we didn't miss any, we could plot these two curves together, cosine 2x plus sine 3x, and the horizontal line, a half. And the points of intersection are exactly the solutions to the equation. Now, interesting, when you do that, you see there really are two solutions. Here's one. Let's see, pi over 4, a little bit bigger than 0.75. This is the solution over here, but we didn't get the solution over here. So in order to get that, we have to actually use our visual observation and say, well, there's another solution between pi over 2 and pi. So if I tell Maple to look for a solution between pi over 2 and pi, oops, that's not what I wanted to do. Here's where this is my graph. I don't need to do it twice. What I want to do is fsolve cosine 2 plus sine, cosine 2x plus sine 3x equals a half for x between pi over 2 and pi. Oops, and this should be a parenthesis, and this doesn't need to be there at all. So now I should get an answer, yeah. And this, which is about 3/4 of pi, is a little bit bigger than 2 1/4, so 2.3 is exactly right. So now I've found all solutions, and I actually had to do some plotting to make sure that I have all the solutions. Problem 3 is to plot some systems of curves. Now, when I have 6x plus 3y equals 10, I could use implicit plot, or I could just solve each of those equations for y in terms of x. So if I have the equation solve six times x plus 13 times y equals 10, solve for y, that gives me this expression. Let me just call this y1. So y1 is this. And I have a second curve, a second straight line. So what I can call y2 is what I get when I solve 9x minus 2 times y equals 3 for y. That's this. And now if I plot together y1 and y2, I get my two lines. When they're drawn to scale, that's what it looks like. Yeah. Second part of this problem, we have two more complicated curves to plot, but they're simply y as a function of x. So the first is a fifth degree polynomial, 2 times x to the fifth minus 107 times x plus 5. And the second is 3/2 to the x power minus 4, an exponential curve. Huh. Well, look how fast. I mean, this thing grows so fast. This is like 150,000. And so let's just say we graph this from -5 to 5. Huh. That's a little bit better. And maybe from y going from minus 1,000 to 1,000. Let's just try that, see what happens. So what you can't see in this is the 3/2 to the x minus 4. Right? Let's go from minus 100 to 100. So this red line is the exponential, and this blue line is the fifth degree polynomial. And eventually this red line is going to be way bigger than the blue line, but probably takes a little while. So down here, the red, that's 3/2 to the x. Yeah, it's going up, but at some point it's going to get bigger than this, but not for a while. And then part C, we have 3 functions to graph together. Plot arctan of x 4 times cosine of x 4 minus x squared over 3. Ooh. So the green is the arctangent. The red is the cosine. And 4 minus x squared over 3, that's the parabola opening down. Very pretty. It's problem 3. In problem 4, we would have to use the plots command. So we have to open the plots package. And we're going to use implicit plot to graph some curves. So implicit plot is the command. And the first curve we should recognize as a circle. X minus 3 squared plus y plus 5 squared equals 36. This is a circle with center at 3 minus 5 and radius 6. So if I let x go from minus 3 to 9 and y go from minus 11 to 1. Oops. Minus 11 dot dot. There we are. That's the graph of the circle. Part B is an ellipse. It's x squared over 4 plus y squared over 25 equals 1. X goes from minus 2 to 2. Y goes from minus 5 to 5. It looks like a circle, but you see it's not drawn to scale. This is 2 units horizontally and 5 units vertically. So if I right click and go on scaling constrained, now we see it drawn to scale and really is this lovely ellipse. When we have x squared minus 9 times x times y minus 20 times y squared. Oops. What happened here? This is x squared minus 9xy minus 20y squared equals 1. And to plot that, we use implicit plot, of course. And I'll adjust the x and y's later. Let's say x goes from minus 5 to 5, y goes from minus 5 to 5. And then we'll look at the graph and see how we have to change it. Well, it's not so bad. This is a hyperbola. I can just leave it like that. Lovely hyperbola. And part D is almost the same, except this minus becomes a plus. What we get is actually 2 parallel lines. And the reason is suppose I try to factor this. It factors. So x minus 4y times x minus 5y, that product equals 1. That's a nice segue into the next problem, which is problem 5, which is factoring. So the command to factor a polynomial is factor. So if we factor x to the 6th minus 1, that's what it is. If we factor x to the 6th minus y to the 12th, that's what it is. And for an integer, the command is I factor. I stands for integer. I factor the number 36363636. Let's see. How many sixes are there? 1, 2, 4, 5, 6. 1, 2, 3, 4, 5, 6. So I think that's the number. It's clearly divisible by 3, but that quotient is 2 other factors. And if we want to factor the very big number, 2 to the 2 to the 6th plus 1, it does factor. Let's see what that number is. Ooh, 2 to the 2 to the 6th plus 1, that's this. And it factors into this. Not obvious at all. Problem 6 is to solve graphically a certain 4th degree polynomial. X to the 4th minus 12 times x cubed minus 46 times x squared plus 12 times x plus 45. So this equals 0 where the graph crosses the x-axis. And so here is clearly one place where it crosses the x-axis. It's somewhere near 15. To solve it graphically means we graph it around 15. Say x goes from 14 to 16. So it looks like it actually crosses the x-axis exactly at 15. If I make this 14.99 and this 15.01, yeah. So it looks like one solution is x equal to 15. Now, the rest of the graph is somewhere here. Suppose I want to blow this up. Let me just graph this from -5 to 5. So I see there are actually 3 solutions. Truthfully, they look like they're -3, -1, and 1. And to just check if that's the case, you can blow up the graph. Suppose you graph it, say, from -3.01 to -2.99. Yeah. -3. And if you do the same thing as -1 and +1, you'll find there are the solutions. And if you want to check, you could just say, okay, solve this equation equal to 0 for x. Let's see what happens. Yeah, you get 15, 1 minus 1 and minus 3. That's what we expect. Problem 7 is the same thing to solve graphically the equation arctangent of x over 2 equals cosine x. So if I plot those two curves, arctangent of x over 2 and cosine of x, that's what it looks like. And the arctangent, going way out, suppose we do this a little bit bigger, say x equals minus 4 times pi to plus 4 times pi. So yeah, it looks like the arctangent just crosses the arctangent's the red curve, just crosses the cosine here and here. And here it's not clear whether this is 1 point or 2. And if we're going to solve this graphically, we're going to blow things up like this is somewhere a little bit less than pi over 2. Let's just say we graph this from 1 to 2 and see what happens. Yeah, so we're just blowing this up. If I graph this from 1 to 1.2, this point of intersection is around 1.06. Yeah, somewhere right there. I can get this better and better and better. Oops, went too far. Yeah, so this point of intersection over here is around 1.0612. And what about over here? Is that 1 point or 2 points where the curves intersect? So this is a little bit less than pi. Let's just start graphing this maybe from -4 to -3. Aha, a little bit too far to the left. I'll make this -3.2 to -2.8. Yeah, so you can see here the red curve is actually crossing the blue in 2 places. One's right around there, and the other's right around there. So if we want to get this to several decimal digits of accuracy, let's see, this one is between -3.2 and -3.1. In fact, we go -3.12, yeah. So we're homing in on this. This is like -3.11 something. Yeah. Between -3.112 and -3.111. And this is between minus 2.9 and minus 2.8. Let's see. Yeah, in fact, you can see it's roughly between minus 2.88 minus 2.86. Oops, too much. Make this a 5. Yeah. Yeah, so minus 2.859 something. Anyway, that's how we solve the equation graphically. It's fun. Problem 8 is to compute some limits. I won't do all of them because they're all the same syntax. So if we want the limit of the sine of 7 times x divided by 8 times x, as x goes to 0, so we're at x equals 0, equal. So this is just going to write the problem because there's a capital L. And if I write the same thing, but with a lowercase l, I should get the answer, which is 7/8. If I take the limit of the nth root of 3, so that's 3 to the power 1 over n, as n goes to infinity, comma, the limit is 1. And if I took the limit of the nth root of n to the 7th, which is the same as n, to the 7 over n, that's it. That's the nth root of n to the 7th. Oh, that's also 1. It's very nice. Problem 9 is to compute derivatives and integrals of some functions. So if we have the function f, x goes to 2 times x to the 5th minus 107 times x plus 5. The derivative of f at x is that. And the integral of f of x again, the integral command has 2 versions, capital I and lowercase I. And the first presents the problem, and the second, the lowercase I, gives you the answer. Let's do another one. Suppose we have the function exp of x, that's e to the x times ln of x. That's a hard problem to do. Let's see what Maple does. Oh, wow. Well, it's complicated. It says it's e to the x log x plus this expression, which is some complicated function. It means that this one really is too hard to do by hand. Problem 10 is to compute the tangent line and normal line to a certain curve. Let me write this as a function. F of x is the square root, SQRT, of 17 minus x squared. And just to see what it looks like, suppose we plot f of x. Now, this only makes sense when what's under the square root sign is greater than or equal to 0. So that means x squared is less than square root of 17. It really just goes a little bit from -4 to +4. So let me just say from x equals -4 to 4. There we are. And if I want it to scale, that's what it looks like. What is the tangent line? I'll just call it TL for tangent line. It's the derivative of the function at 2 times x minus 2 plus the value of the function at 2. So that expression is the tangent line. And the normal line is a slope. This is perpendicular to the tangent line. So the slope is the negative reciprocal of the derivative of f at 2 times x minus 2 plus f of 2. And so suppose I plot together f of x, tangent line, normal line, x goes from -4 to 4. Perfect. Let me do it to scale so it looks right. There we are. So this is my curve. The blue is the tangent line. The green perpendicular or normal to it is the normal line. Problem 11, we have a polynomial of degree 4. Actually, it's exactly the polynomial we had looked at earlier. So let me just copy from the previous problem. So let's call this f again. X goes to that's the polynomial. And we want to find the x and the y intercepts. Well, we already found the x intercepts. Oops. X equal minus, what were they? Reason to do it again. 15, 1, minus 3, and minus 1. So minus 1, minus 3, 1, and 15. And the y-intercept is just the value of the function at 0, which is equal to 45. Yeah. Okay, anyway, x and y intercepts we have. This is 45. And local maxima and minima, points of inflection, and so forth. So this should all be pretty routine by now. The critical numbers are the places where the derivative, let's say f solve, derivative of f of x equals 0. Solve for x. We have 3 critical numbers. If we take the second derivative, that's the second derivative. And if we take the second derivative, and evaluate it at these critical numbers, so this should say, evaluate the second derivative of f at the nth critical number, and we get positive, negative, positive. So relative minima at, let me just emphasize this. So here's the critical number, and here's the second derivative. So where the second derivative is positive, you have a relative minimum, minus 2.18 and 11.05. And a relative maximum at 0.12. So minimum, maximum, minimum. And the points of inflection, you can just look. Oops, this should have this. And if I look for the places where the second derivative is 0, these are the inflection points. And I know this is concave up, concave down, concave up again. So you can write that all out. This is problem 12. Let me separate these. This is problem 12. Hey. So we have a sequence defined recursively as follows. U1 is equal to 1. U2 is equal to 2. And for n from 3 to 20 do, I put in my n do so I don't forget. Un is determined by the two previous terms of the sequence. It's 4 times u n minus 1 minus u n minus 2. So here are the first 20 terms of the sequence. What about problem 12b? Compute the smallest positive integer n such that n squared minus n plus 41 is composite. That means not prime. So let's just try, for example, for n from, I don't know, 1 to 60 do. And what is it that we want to do? If, see, I don't want to know whether n squared minus n plus 41 is prime. I want to know when it's not. So if not is prime, then print n. So if n squared minus n plus 41 is prime, this statement is false. If it's not prime, this statement is true, and then n gets printed out. So up to 60, these are the n's for which this number is composite, is not prime. And the smallest is n equal to 41. So that's the solution to the problem. problem 12C, compute some limits. So this is an iterated loop for M from 1 to 6 do, and for N from 1 to 6 do. And I have to end each loop separately. And what is it that I want to do? I want to find the limit of sine of M times X divided by sine of N times X as X goes to 0. Only this is just I just want to write this, I, and that's it. I want to print this out. Ooh, there they are. So here M is 1, so it's sine X in the numerator, and the denominator goes sine X to, now here, why is this 1? It's sine X over sine X, it's 1. That's what the output looks like. And then the last little programming problem. Problem 12D. Find the smallest positive integer n such that n to the 1 over n is less. So we know that this is just to make sure everyone understands the basic calculus. If I take the nth root as n goes to infinity, oops, let me clear the memory because n is confused. There. Yeah, the limit is 1. See, I had to go back and clear the memory because from the previous problem, it thought maybe n was 6 or 7. So we know that this is getting closer and closer to 1. So at some point, it's certainly less than 1.001. So let's just make a loop for n from 1 to 20 do. And do. And let's say if n to the 1 over n let's write that as a decimal, is less than 1.001, then let's say we print n. Oh, I'm sorry. So for D, so this is E. Let me start with it. Let me just say I'm doing E. Yeah. One, huh? That's not too exciting. Suppose I start with 2. So 1 to the 1 over n is 1. But when n is 2, square root of 2 is 1.4. Cube root of 3 is bigger than 1.01. So I should have said, compute the smallest integer n greater than or equal to 2. Yeah, because when this is 1, it's not too exciting. So suppose I go up to 200. No. Interesting. So the first time this is, I'm going up to 20,000. Let me stop this. This is too big a calculation. So let me just, I know what the answer is. So let's just go for 2 up to 9,130. Yep. So the answer is n equals 9,124. So I should have said that this be n bigger than 1. And let me just go back and now do problem 12D. Again, I'm looking at exp of 1 over n, e to the 1 over n. Oops. Okay, let me clear the memory. Yeah, so that limit's also 1. And it's basically the same program, except it's e to the 1 over n in here. And let's just go from 1 to 100. Nope. Let's go up to 1,000. Go up to 3,000. Just over 1,000. So let me stop this calculation. Yeah, and let's just test. EVALF, what is e to the 1 over 1,000? Oops, need a second parenthesis. It's bigger than 1.001. But if I compute 1.001 e to the 1 over 1,001, it's less and 1.001. So this is really the first time that this curve falls below the x-axis. Okay, let me save this. This is Math 156. Homework 11. Final exam review problems. And I think I will stop here for now.